Okay. All right, everyone. Welcome to the last Tuesday lecture of fall 2025, CSE466. And today is going to be a little bit of a slightly more dry and boring lecture just because we're essentially going to review all the content for the final that you guys have looked at since the midterm. And so if you haven't seen it already, I posted a final exam review thing in Discord. It's in the announcements channel right now. And it's basically everything from the midterm review with all the greenbelt material just stapled onto the end. So let's get started. Let's see. Hopefully that doesn't break anything. Cool. Okay. So just two administrative notes to be sure of. Make sure that you have your ASU ID linked on pwn.college. It's worth double checking this. Just make sure that it's there. If it's not there, we literally can't give you a grade because we don't know how to associate your pwn.college activity with your ASU identity. This is mandated for the connection to happen. And then also, final deadline for all your challenges is December 15th at noon. So it's 12 p.m., not midnight. And it's like that because grades are literally due midnight on that Monday, December 15th. And so we give ourselves 12 hours to figure everything out, essentially. I guess, does anyone have any questions about that end of semester administrative stuff? Okay, cool. Final. Hopefully you all heard the details by now, but it's the same time, same room. It just, instead of ending at 5:45, it's all the way to 6:20. So you have more time to take the final exam. Basically same terms as the midterm, show up on your registered class days so we know who's in what session. You're allowed one 8.5 by 11 handwritten cheat sheet. Don't OCR, don't try and use a handwriting font, etc. Yeah, use your cheat sheet wisely. Also, this exam is cumulative, so it's covering everything that we've done in the course. That's yellow belt and green belt material. Finally, grading will be stricter than it was on the midterm. As on the midterm, we were trying to give people the benefit of the doubt as much as possible. On the final, we're crunching it a little bit more. Basically, don't make three statements and one of them is true and the other two are blatantly wrong. We'll be looking for things like that. And then finally, just to give you an idea of what's on the exam, just you can expect a roughly 50-50 mix of yellow and green belt topics. So that's 50% of things that you've seen already that potentially could have been covered on the midterm, 50% new material from those green belt modules that you've been kind of working on. So pretty much what we're just going to do is go through all the green belt side of that little review sheet. And pretty much I'm just going to be asking questions. We're going to be discussing. We're going to be figuring out where the knowledge gaps are. And pretty much this is just an opportunity for you guys to clear up anything that you're unclear of. And then also, if time permits, I have some microarchitecture demos to go through. So simple. So now we get to turn this into more discussion. So basically, I want to ask all of you, what does chroot actually do?
It changed the root.
It changes the root directory. So when you chroot a process, you are basically redefining what that leading slash means. So therefore, whenever you reference an absolute path, it's going to use that updated definition for that slash. Now, what is the proper way to chroot a process? Obviously, there's wrong ways to do it. We've discovered wrong ways of doing it. What about proper ways? Exactly. So we have to be able to chroot into our jail, right? And then you actually have to physically put the user in the jail. It doesn't make sense if you just build the jail cell and then just leave them outside. So you have to make sure you actually get your process in there by chduring to an absolute path that's deeper into the jail. Now, what other ways can you break out of a jail? So let's take that one example. Let's say that we've chrooted and we've chdured in. What are some ways that we can get out?
You could make another directory below you, use chroot to make that other directory the new root, and now it'd be free to get back up.
Yep. So just to repeat for the stream, basically, someone said you can make a directory in your jail and then chroot there. So now the jail is deeper than where you actually are. This allows you to relatively traverse back up to the rest of the system. Now, my question back to you would be, what does that imply about this process? What do you need for that process to be possible?
You need code.
Well, you need code execution, but what else do you need to chroot?
Root permissions.
It's root permissions. So you can do that where you take another directory, you chroot, basically you move your own jail, but this requires root permission. So this also requires you having arbitrary code execution, which we know how to get arbitrary code execution in this class. We also, at this point, technically know how to escalate the privilege of a process by using kernel bugs. So 2 and 2 together, you can break out of chroot. Now, can anyone think of any other ways to break out of a chroot jail? Like, let's say that there's maybe other things that we've done in this class that like get you out of chroot, or at least bypass this. So what about file descriptors? What happens if I have file descriptors and I jail a process and then I don't close all the file descriptors?
You can access those file descriptors through your process.
Is the slide supposed to be on the title? No. Is it broken? Let's do, no, not like that. Let's do that. Okay, so yes, if we leave open files before chrooting, we can access those file descriptors. And if those file descriptors, if they're outside the jail, they're outside the jail. Like we can still reference them. So it's important that when you jail a process, you need to be closing those. Are there any other ways to get out of the jail? So one person in Twitch chat says that if chroot is somehow using the same file system, you can exploit that. I'm assuming what they're meaning is it's still broken. Hold on. Oh, it is broken. Why is it broken? All right. Yeah. Let's do that. Let's do that. I need to put it behind me. There we go. Hopefully that should work now. I'm watching for visual confirmation that it's working. Okay, I see my slides. I'm gonna go back to this slide really quick just so Twitch chat can see it. Basically just screenshot that, read it, understand it. Yeah. Okay. So any other final questions about chroot? Like this is a pretty simple one, but you guys should know about this. So next, talk about setcomp. What does setcomp do? Who's got a definition for me?
Restrict syscalls.
So it restricts system calls. And so when we setcomp a process, like we basically can either define like an allow list or a block list. Basically, we can essentially filter what syscalls a process is allowed to make. So many of you have probably experienced the exact situation where you setcomp a process and make it so that the process can't write. Call the write syscall. What happens then when you try and print in this process?
It explodes.
It explodes. And so, yeah, it'll kill your process when you make that write syscall unintentionally. Similarly, like, I guess like my then question would be like, if you're an attacker looking at a setcomp process, like what are the considerations that you have to make? Like, what does this mean for you? And I guess like this obviously flows into the third question, which is just like, how do we bypass this? Like as an attacker, like if we're dealing with a setcomp process, what are some things that we can do?
Side channels.
So we can side channel. That's one acceptable way of going around it. What other ways can we work?
arch32 syscalls.
Sorry?
arch32 syscalls.
Yeah, so we can use different architectures. We can look at basically how the rules for setcomp are defined. Like I've done CTF challenges where they basically try and block all the syscalls, but then say, oh, syscalls above this really large number are allowed. And it turns out if you feed really large numbers into RAX and make syscalls, you can still actually get to the syscall handler because it only checks the lower bytes. So there's interesting ways to go around it. So there's one other kind of approach that I'm looking for that I'm still not seeing.
Modify the setcomp use themselves and like task.
Okay, yeah. So it's jumping a little ahead a little bit, but we can kernel exploit, like we can just disable setcomp on our process. That's one thing we can do. The last one I think is definitely worth bringing up, just because like I like solving puzzles personally, is if you have a setcomp process and it allows certain syscalls, there's probably a way to do what you want with those syscalls. For example, if I disable the read syscall only and say you can't read data into this process, I can still open a file and mmap it into my process, for example, to have access to that data. So there's more than one way to do like all of these computational things, or at least most of them. So anyone have any lingering questions about setcomp? Got it. So now, one thing that I also think is just funny and important to look back on as a student is how easy a concept like setcomp feels now. Like you've been through a lot. So the next thing I want to talk about that may or may not be covered on the file is the proc file system. So this is something that we haven't explicitly written challenges about, but has sort of slowly started to show up more and more and more as you guys have been getting deeper and deeper into these concepts. And so my first question to you would be just what is in the proc directory?
Information about processes.
Yeah, so it's information about processes. It's basically a way to interact with like data structures in the kernel, data structures like for your process, get information about what's going on your computer. And so it's a virtual file system, and everything there is just files that are constantly maintained and backed by the kernel. So they're not real files on your system, rather just a virtual thing that's mounted in. And if you look at the mounts on your system, like right now, then you could go and see that proc file system mounted in. And so what are some ways throughout the class that you guys have used the proc file system? So for example, like the easiest and low hanging fruit would be that you can access like information about processes. So you can go, okay, proc/pid/maps, and then you get a mapping file that says, okay, here's all the shared libraries, here's all the objects that are mapped and where they're mapped in this process. What are some other things that we've done with the proc file system?
View the open file descriptors.
Yeah, so you can view open file descriptors. What else do we have?
The old like root directory, if we like change root and it will still like be somewhere and check the proc.
Yeah, so every process stores its root directory basically as a symlink in that proc file system. So if you have access to it and you can get access to another proc file system or other procs, I guess, file system, I guess like just directory, I guess. I'm not sure the word there. But if you can get access to another process's directory, you have access to what it thinks the root file system is, which, by the way, when you chroot, you update that definition in proc. So if you have root access, you can use it to jail escape, essentially. Like if proc is for some reason mounted into your jail, or you have some other way to get to it. Are there any other cases that you guys have found proc useful? Like there's so many interesting little tidbits in proc that I would just recommend when you're bored one day, just go looking.
Proc algorithm.
One and then two. We'll go do both.
Sure.
Okay.
Proc algorithm.
Yeah, so proc kl sims is something that in the kernel, basically we can use to figure out the symbols of kernel addresses, or the addresses of kernel symbols, in cases where KASLR is disabled. Also, when we have root privileges to read it. Then,
Changing namespaces.
yeah, changing namespaces. So namespaces are also like managed and kind of exposed via the proc file system. And so really just something that you should poke at, be a little bit familiar with. Obviously, on the exam, it's not going to be list 27 uses of the proc file system, but you should at least be roughly familiar with like, okay, hey, when I type VM map in GDB, this is what it's doing. Like that kind of thing. Like what, like the most common like use cases. So the last thing for sandboxing is namespaces. So who can give me like a rough definition of a namespace? 'Cause I understand it's a pretty abstract concept. Anyone?
Maybe it's like all the ways the kernel can lie to you. It can lie to you about like where you are in the file system. It can lie to you about what file descriptors exist. It can lie to you about like what processes exist.
So I actually don't hate that definition. And it's kind of right. But basically, like namespaces are the way that your kernel maintains like essentially separate sort of the word containers is misleading, but essentially you're looking at like different sort of almost like regions for processes to exist. So you could think of a mount namespace, right? Where you say, hey, processes in this namespace can access this mount, processes outside this namespace cannot. And then remember that processes are hierarchical. So you have a parent namespace. And so it's kind of like layered. And so essentially when we want to isolate a process or isolate a series of processes or isolate a network, basically isolate anything, we can use namespaces. And functionally, like the core definition of this is like kind of buried in the name a little bit. Like namespaces is essentially there to prevent naming collisions, like when these things happen. And so the second question I have here is just what are some ways to abuse or escape like improperly constructed mount namespaces, since that's what we did challenges on. So there's namespacing challenges. How do we break out? I know at least one of you did some of the namespacing challenges.
That's same as the one before SecComp. Is you have like you have open file descriptors, you can do stuff with them.
Yeah. So basically, if you don't clear your file descriptors, like then you're going to run into cases where you can have a file descriptor that goes outside that namespace. Anyone else?
you could have a migrated home directory of that has the flag in it.
Yeah, okay. We could mount the flag into the namespace by accident. That is something we did do in one of the challenges.
Good job.
You probably know the whole file system. Some of you do that version file system.
That is very true. So I'll give you a funny story. That was a totally Rob approved namespace definition. Thank you, Rob. So I'll give you a little anecdote here. So on ASU campus, we had the ASU Hacking Club. And in order to get into the ASU Hacking Club, you have to go solve, or you at one point you had to solve a membership challenge on their website. And as part of this membership challenge, it was basically just like a basic, like the program's running in a Docker container, like on the web server. And then basically you go and you pwn it in the Docker container. And then there's a file in the Docker container that you can write basically your little like key into to prove that you solved the challenge. However, it turns out that this was mounted into a directory, and this directory was mounted in from the root file system. And so this very quickly led to a case where I solved the membership challenge, and then I have root permissions, and then this folder is mounted in from the actual, like basically like underlying server running this website. And so I could fill up the disk or make a file that's literally only deletable by root. And then it's annoying to get rid of from like a web server perspective. So that was one interesting way that actually happened. Granted, not security relevant because it's running on a crappy web server, but still funny. So I guess before I round out, like any questions on sandboxing, like these are the kind of the broad things that you should expect to see for sandboxing on the final, like chroot stuff, setcomp stuff, like /proc stuff, namespaces, like these are the main things that we touched on in sandboxing. So if you're going to see exam questions about sandboxing, it's probably going to be roughly like in these disciplines without going crazy on details. Okay. So next is race conditions. Still probably my favorite module just because I think race conditions are cool. Although I think sandboxing is actually my favorite module. And so first question is pretty simple. Like, what is talk to? Like, what does this stand for? What does this mean?
Time check, time of use, where basically between the time where something is checked against, say, some arbitrary value, and the time where it's actually like used within a function, if the thing being used is changed, then it can exploit vulnerabilities.
Yeah. So essentially we have a check, we have a use, and in between those two times, in many cases, we can mess with what is being checked and what is being used. And so we've seen this in a number of different cases. So for example, like file system races are generally like time of check, time of use based. So you could think of, okay, I'm checking if this file is a symlink, and then I'm opening it. And there's a window for you to mess with things. And so one thing that I think is important is like understanding, okay, so like we know how to abuse time of check, time of use. Like you have a window, you're looking to exploit it. And so the question would be like, okay, well, how do you actually fix time of check, time of use? And there's a couple different ways to do it, but I'm curious, like, does anyone have any ideas on like maybe like as a developer, like how we can sort of dodge this problem?
Semaphores.
So yeah, we could use a semaphore. But let's think of like the base case in terms of like a file system, right? Like what's something we can do instead of checking the file and then opening it?
Like just use a file descriptor.
Yeah, so we can literally just use a file descriptor. So therefore, instead of checking and then starting to use, we can open it, then do our checks. And so basically we flip that ordering around. And so now the use happens before those checks. And so even when the checks pass, we can continue using it without risking basically the underlying resource changing out from under our feet. There's other ways to do this, like, but generally like file descriptors are a great way. Like you can also use semaphores, like basically just when you're using the file system though, semaphores are not going to work. Just because like your file system is potentially able to still race. I'm actually not 100% sure on that, but would be interesting to find out. And so to extend to talk about file system races, like I've talked about time of check, time of use as ultimately the reason for file system races happening. And you can use file descriptors to sort of dodge this, but I think sort of the big question is, well, we know what causes them. And so I guess let's just go with what are ways that we can increase our chances of hitting a file system race? And so generally, like you're racing, you know that like, let's say you have your script that flips like some like temp A file back and forth between some random file and the flag, right? And so you're not hitting this race. Like, what are some ways that we can potentially try and make this easier for us, or just what are the knobs that we can mess with?
You see yours on.
So you want, okay. So one solution is to race faster. Now, we talked about racing faster, but what does racing faster mean? It means that our timing windows also get tighter, right? And so rather than racing explicitly faster every single time, like one thing that we can use is we can use multiple processes. But multiple processes, if you start them all at the same time, like you kind of have this like cascading like time window. I guess, can do I still this is my history? Yes, I do. So remember that, let's see, it's, yeah, so we just need to race faster, right? Like we're back here again. And so just because we can race faster doesn't necessarily guarantee that we're going to be passing that check. Rather, the way that we want to race is essentially by, we can either use multiple different threads to essentially like stagger out, basically giving ourselves more window to hit that race. What we can also do is look at offsetting that race a little bit. So if we know that like the check is going to happen maybe at like times 1 and time 3, and then we know that our little like our own script is never going to hit that, if we offset it just a little bit, we can like increase that. Like I think I always like to think of it as like you have like two standing waves, you're like bringing them together so they like overlap perfectly. Like it's just a game of just like slightly nudging one to one side. And then finally, just like how can we mitigate file system races? Like we talked about it already. They're using file descriptors. There's also things like using that, I think it's like no follow to make it so that like things don't follow symlinks. Basically just protecting yourself and knowing that this is something that can happen. Next, we have data, shared memory races. So who can tell me what these are?
You have like multiple threads accessing the same piece of memory.
Exactly. So basically this just happens when you have, you could think of it as like two threads of a process, like two processes. Basically you have two pieces of code that are executing at the same time that are sharing data somehow. Generally the shared memory is like the way this happens. And so what is the problem with this? What happens?
Depending on the order the thread executed, you get different like behavior.
Yeah, I mean, ultimately, like if you were both, like if you have two cooks in the kitchen and they're both trying to use the same salt shaker, you're gonna have times where one chef reaches for the salt shaker while the other one's actively using it, and then you run into problems. And so this results in things like updates being lost or updates being like applied twice in error. This you could think of this in like a more dangerous scenario rather than just like leveraging like just like a basic like integer, right? Like maybe we're sharing heap pointers back and forth between these processes, and then you can get a double free. Like so these like data race conditions are very pernicious when they do happen. And so one other question that I have up here is what is a critical section, which hopefully everyone knows. Remember back to that operating systems class you all took.
It's like the section where, say, in like a shared memory, you'd want one writer, or like you wouldn't want two writers at the same time, or a writer and a reader at the same time. So you can use like a semaphore normally to fix that. And that's actually where semaphore should be used.
Yeah. So ultimately, like to summarize, like a critical section is when you are actually interacting with that shared resource. Like when you are reading or writing from a shared resource, you want to make sure that like that like read to use, reuse, write back, like that process is uninterrupted. And so that's generally when we leverage things like semaphores, like mutexes, like these multi-processing features that basically say, hey, don't interrupt me when I'm doing this, and don't let that person interrupt me when I'm doing this. Question.
Is the critical section part of the code, or is it the actual shared memory?
Sorry, can you repeat?
So like when you say critical section, do you mean the code where it's accessing the memory, or are you referring to the actual shared memory?
Oh, the code work. So like the critical section is like the section of code where that access and use is happening. Like the actual instructions that are being executed. You could think of like if you have a program that's using a semaphore correctly, then that region that the semaphore is locking down is what we call the critical section. Got it. Okay. So now let's get into the fun part. Actually, I guess like, does anyone have questions about race conditions before I wrap up? Like, once again, pretty straightforward. I did a pretty good lecture on this, I think. All right. So now let's get to the fun one, which is microarchitecture. And so now we get to ask the heavy hitting questions, such as what the heck are transient instructions? Can anyone tell me?
Instructions that that can be executed without order.
So kind of yes and no, because I guess it depends. But basically, so a transit instruction is an instruction that's essentially like executed in error by the CPU. So you could think of the CPU speculates and says, okay, this branch is going to go one way, and then it starts executing instructions basically because it's assuming that the branch will go that way. And then we actually get to the branch and it goes, oh crap, I have to go the other way. And so all these instructions that it's executed speculatively, we call these transient instructions. Basically because they are going to be unwound, like it's going to be flushed out. Like basically their effects will never actually hit the architecture, like the visible state of the CPU to our program. So like you could think of like if you speculatively execute like move RAX 60, that's not actually going to happen like once that instruction is flushed out because it's discarded. However, these transient instructions have microarchitectural state impacts. And this is the big thing that happens with these microarchitecture attacks is we transiently execute some instruction and then it has measurable effects that our process can't see, but we can measure as cool hacker people, essentially. And so the question then, I guess, like my second question to all of you would just be why? Like, I guess I've already kind of said it, but like, why can transient instructions be exploited in this nature?
Because they touch the cache.
So they touch the cache, but there's like, essentially they touch that microarchitectural state, and that can be probed and measured. And so it's essentially like leaving footsteps in the sand almost, like you can kind of like eyeball it. Snow. No, we're in Arizona. They don't have snow here.
I mean,
Black stuff is real.
Yeah, Arizona's not real actually. But essentially these transient instructions, like they are being speculatively executed, they're being out of order executed. Like you could think of in the case of meltdown, like, right, you're trying to access like unprotected or not unprotected, just like invalid memory or access protected memory that you can't read. And then out of order, it still accesses that memory and then puts some information in the cache, maybe because that value is used in some way. And so those transient instructions, like they have basically that underlying microarchitectural state, like updates, like changes to it without actually hitting the physical, like visible state to you as a process. And so let's talk about flushing and reloading. So first off, flushing and reloading is not an attack, it is a technique. And so how does it work?
You flush the cache.
Okay.
You get the whatever the victim, I guess, is to go to do something that would put the value into the cache, and then you go try to load that same value from the cache.
Mm-hmm. And then how do we get information out of this?
You time that.
So we time it, right? And then what?
Whatever the shortest one is, or the one that like is significantly lower than the rest, is probably in the cache.
Got it. Okay. Probably. Yeah.
Probably.
And so just to really go over this, because I think it's important, because if you don't understand flush and reloading, then you have no hope of ever understanding Spectre or Meltdown, which is essentially you have a cache, and we hopefully all know how a cache works at this point, but essentially it's storing these accesses like very close to the CPU so that it doesn't have to go to RAM every single time to fetch, which takes a very long time. And so when we flush the cache out, we basically reset it to a blank state, and then we let the victim process just do its thing. And then we can observe what happens after the victim process performed those actions. And so even though we have no visibility into the actual program state of this victim process, it leaves behind these microarchitectural breadcrumbs that we can pick up and then measure, and then essentially use those to exfiltrate data. Now, the way that this works is a little bit complicated in implementation, right? Like you all hopefully like started doing some of the microarchitecture challenges, like doing this, even just like basic like flush and reload to measure cache timings is not easy, right? Right?
Yes.
Okay. And so I guess like I want to dive like a little bit more concretely into this process just because it's a little bit important. And so when we flush cache, like, so what am I trying to say here? What's the right way to ask this question? So I guess like when we're measuring, like what are we actually doing? Like what's the technique that we've been using to measure something in cache? because we can't just like look at the cache and go, okay, that's the value, right? We have to be a little bit more intelligent about how we pull that value out. How have we been doing that?
RDSDC or RDTSC.
Well, that's just measuring the timing, right?
Yeah.
Memory access.
Well, so we can time memory accesses, but the idea is that we're timing a lot of memory accesses over different rows of the cache, right? And how are we doing that?
Number of tick.
Like each page, maybe.
Yeah. So like we make a massive array and then we split it up basically by page size, right? And then we can essentially make that assumption that like this cache row is representing this page. Like that's heavily simplifying things, but that's what we've been doing. Like we've been making this massive array of like 256 different slots that are each an entire page wide. And then we're measuring based off of that which timing was the lowest. And that tells us like which cache row was actually touched by that victim process, right? And that's what's enabling us to actually leak out data. It's not just we're looking at one cache row and going, okay, they put a P there, and then we read the P, right? It's not that simple. And so we have to use this method of basically constructing this massive array. Nothing. Question, what are some mitigations against these transient cache attacks from the Twitch chat? So there's some very interesting like white papers you can read. Basically, like I would recommend if you're actually interested in like what the defenses are for these things, to just go read the white papers about them, because these patches have been implemented like broadly and pretty studied, because people were really upset when they came out that like everyone lost like 10% performance on their CPUs. And essentially it's just enforcing more guardrails to make transient execution like less, essentially like I wanted to say like less useful almost, where you could think of in the case of Meltdown, like we're abusing out of order execution. What happens if you just remove out of order execution? No more Meltdown, but also significantly slower CPU.
Just remove the cache.
Yeah, just remove the cache. Okay. So does anyone have any questions about flushing and reloading? Okay. We'll dive even deeper. So let's talk about Spectre. Yeah. Spectre's going to be on the final. Well, microarchitecture will be on the final. Spectre's part of it. So what is Spectre? Anyone?
Is the branching the state machine and the branching of CPU to like trick it into execute a transient instruction?
Literally, quite literally, yes. And so basically what she said was Spectre is basically this idea that we have some kind of prediction that happens when the CPU needs to branch. And we can abuse this prediction to cause the CPU to transiently execute instructions in the name, like Spectre, speculative execution, almost. And so by doing that, by forcing the CPU to execute transient instructions, we can basically always force those cache updates to happen, or at least in theory, always force those cache updates to happen. And so so once we do this, like we're essentially getting to the same place as flushing and reloading does, except now we are the ones that are in control of when this speculative execution happens. And so we're using this basically to weaponize it against another process. And so who knows the difference between Spectre V1 and V2? So, because they're both pretty similar, but they're exploited in different ways. They use different mechanisms. Yes.
V1 abuses direct branches, whereas V2 abuses indirect branch jumps.
Yeah, no, that's correct. So basically the big overarching difference is that Spectre V1 is when you have conditional branches. So this, you could think of this as like a standard like if else, right? So you're either going to go down one of two branches in most cases. And the way that we do this is we prime by repeatedly going down one side of this branch. And so you could think of like, okay, we're checking if like an array index is in bounds. It's like the obvious example. And so we access like random indexes, like we continually prime that branch to go down the, yes, this is valid side. And then you send it index 200,000, and then it speculates because we're predicting that branch predictor to go down that side. And so we have those transient instructions that get executed. And so therefore we can index into this array at index 200,000 or something like that, or some other kind of primitive that essentially does the same thing. And then by doing that, we can observe the state of that. Yes.
So if it starts executing transient instructions and it's doing like some crazy invalid memory access, will the program fail, or will it be the cache start set on?
Well, it's never actually going to segfault. Basically because like so you can think of like, I'll jump ahead a little bit, but so meltdown happens in this way, where basically we have a sequence of instructions where we start out with saying, I want to access memory address 1337, right? And this segfaults because 1337 isn't a mapped address. But what happens is that these instructions start executing out of order. And so transiently, this memory access happens. It doesn't matter if you can access it or not. If it can get there, it can get there, and it will transiently execute that. And then once it figures out that that memory access is invalid, that's when it's going to start to unwind and sort of flush that pipe out and then make sure that none of those effects hit the architectural state of the process.
Okay.
And so in Spectre, when we access like memory that's like clearly way out of bounds of this array, like it's not invalid in the eyes of the program because it's like the CPU is just doing what you tell it. Like you're the one responsible for putting those boundaries in front of it. So as long as we're not like page faulting and it just can't access the memory address, like as long as you can get there, you can get there. And so for V2, rather than dealing with a conditional branch, we deal with an indirect jump. So good question, trick question, not a trick question. What is an indirect jump? Anyone? So an indirect jump is essentially when we have some like funny guy in our C code that's like not supposed to be there, right? And it's like call and then a pointer. So you can think of like, for example, let's say that we're like in a logging application and maybe we have a struct that defines a logger and then that logging struct has like function pointers in it. So you can think like, okay, here's the write function for this. Or heck, one thing that you guys have seen very recently is kernel devices, right? Kernel devices have a function, like a table of functions in them, like called file operations. So like one for reading, one for writing, one for ioctl, like etc. And so when those are called indirectly, like when we literally say, hey, call the function at this location, or sorry, call the function that is, that's hard to describe in words, but basically call rex, and then rex contains a memory address, right? And so rex can be anything, essentially. Like rex could be one, rex could be some valid address, rex could be a completely invalid address. That's the indirect nature of it. And so there is also, as you said earlier, basically a prediction mechanism for these indirect jumps. And specifically, you can go and look at it. I believe it's like 29 indirect jumps or something like that are stored. But there's a specific like kernel page if you're curious how that works. And the idea is that we can train this indirect branch to go to a specific location. And by basically saying, hey, call this thing, call this thing, call this thing over and over and over again, we can train that branch so that when that indirect jump happens, it speculatively goes to a different location than what is actually going to happen. And so we basically introduce our own sort of artificial branch point. And so this means that if we can train the branch predictor to go to a Spectre gadget and then call it somewhere where that Spectre gadget is actually relevant, we will start speculatively executing the Spectre gadget in the victim location.
Wait, are there challenges on V2?
Yes, there is. I believe, let's see, it's on here somewhere. I believe the Spectre, no, that's not. So I believe Spooky Spectre 2 is Spectre V2. I want to say one of the YPU ones that's not assigned is also a Spectre V2, but it's not assigned.
So
Okay. And so now that we hopefully roughly remotely understand what Spectre looks like how do they leak data? Like how do we actually control this process now?
for the branch predictor into executing trains and instructions, and then it's a matter of just using a flush and reload to access.
Pretty much. And so once again, like when we are speculatively executing, we're putting a value in the cache, and then we are essentially using our massive array to say, hey, that value is going to implicate which cache page, or sorry, which cache row is going to be touched or updated or primed, essentially. And then we can go through and measure every single one, and it's miss, 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 and then we'll hit on one of them. And then using that timing discrepancy, we can then over time sort of build up an intuition of what's going on. So Spectre's complicated. One thing also is that we're going to be going over more microarch stuff on Thursday, so don't completely panic yet. But do start these challenges; they're fun. Also a little bit RNG. So next we'll talk about Meltdown. So does anyone know what meltdown is? Like I've talked about it a couple of times already, but just like high level, like Spectre is abusing basically branching. Sorry, words. Basically, Spectre is abusing the branch predictor. So whether this normal branch predictor or like your indirect jump branch predictor. Meltdown, on the other hand, what is Meltdown using?
Independent chain something.
Independent chain, like so. I guess like to me, I'm thinking like it's like out of order execution essentially.
Yeah, because if there's like a chain that takes longer than the other chain, then it's gonna like perform the other chain first.
Yeah.
Yeah.
And so you can think of this as like, okay, I'm going to access a memory address. Obviously, there's going to be some check at some point to say, hey, can this process actually access this memory address or not? But that's a process that takes time. And so while that's happening, the CPU wants to keep executing things because it's a pipeline. We want to keep going. Like every cycle that we spend in the CPU not doing something in every phase of the pipeline is time and efficiency lost. And so therefore, we try to front load as much of this. Yeah, they both leverage out of order execution, to be clear, but one of them is not speculative, or one of them is not branch prediction based. And so then essentially, when this out of order execution happens, like this memory access that is invalid can happen earlier in the pipeline before it's actually ruled invalid. And so we can essentially see the microarchitectural state effects of this transient memory access being used potentially before it's ruled invalid, and then everything's rolled back or flushed essentially. And so this means that like you could think of like what is a good example for this? You could think of just like a meltdown gadget, like it's literally basically just like one line of code where it's basically like you're accessing an array in like the classic Spectre style, but then you're doing it in a way that's obviously illegal, but then you're hoping that the out of bounds execution of the CPU is going to result in that access still being happen. And yes, Rob from the Twitch chat says Meltdown takes advantage of the fact that some Intel CPUs can speculatively access memory without verifying the supervisor bit. So basically, without verifying that they actually have permission to do so. And then the segfault handler. Yes, I knew that. Okay, that part's irrelevant. And so this once again like results in the same problem of flushing and reloading, where it's just okay. Well, like we can flush the cache. We can then try to do our meltdown thing, which is hoping this out of order execution results in a cache state change, and then we measure. And so just understand this process. Like I would highly recommend doing the meltdown challenges. Like these microarchitecture things are something that you're not going to understand until you just get your hands dirty and really just try and throw your head against the wall for a while. Like that's how you build your understanding on something that's like just not easy to get visualization into. And then we'll also have some demos tomorrow talking about it, or tomorrow, Thursday. So before I completely move on, are there any like lingering like microarchitectural questions?
In Meltdown, would this apply like in a userland process to like kernel memory then? Could you like
Yes.
So you could like just put a kernel address and hope that it gets speculatively executed?
Yes.
Okay.
So if a CPU doesn't, or if it does check for the supervisor bit, it's not vulnerable to meltdown.
I believe so. But it's slightly more complicated than that because it relies on that supervisor bit being checked before. Like meltdown is not like a did they check the supervisor bit or not? Like obviously they're going to check it. It's based on the ordering. And so if that ordering happens in the correct way, then like you're not going to have that vulnerability. But if those instructions execute transiently before that bit is checked, that's the problem area. And as Rob has said in the Twitch chat, older Intel CPUs are vulnerable. Like in modern CPUs, like meltdown has been addressed. Like and AMD CPUs, I believe, didn't have this pipelining bug, and so wasn't affected by this. Like Rob is basically, I'm going to read word for word what he says. Meltdown was a direct consequence of how Intel as a vendor designed some of their chips. Yeah, that's tough. All right, so last little greenbelt module that we're going to have on the final is kernel. So hopefully we've seen kernel enough by now. So first question is a fairly simple one, which is just what is a kernel module? And I guess I'll talk about character devices specifically, since some of you are sticklers. Yeah.
It's basically code that allows you to interact with devices.
Yeah. So basically, like when we plug a device into our computer, like we want some way to interface with said device, especially at a privilege level. And so we write a kernel module where basically we are interfacing with that device and opening up a software interface so that it's essentially a kind of communication layer or translation layer is what you could think of it as. Essentially just an interface to access the device. The device like manages its settings. Like you could think of like device drivers almost. And so that question then is just simply just like when we have a kernel device, why is it expanding the kernel's attack surface?
Like if you don't harden the APIs and test them thoroughly, and there could be vulnerabilities in the APIs that lead to vulnerabilities in the kernel.
Yeah. And so like basically it summarizes like the last 4 words that you said, which is vulnerabilities in the kernel. And that's because these kernel drivers run where?
In the kernel.
In the kernel. So therefore, when there's bugs in these kernel modules, then we have issues that are in the kernel, which is bad. And so simply like it's like we're writing code at like that's running basically at a different privilege level. And so we have to be more careful just in general, because any mistakes that we make here that are blatantly obvious, like software vulnerabilities, become kernel vulnerabilities. And so just very simple. So then also I made us think about this. So I'm going to make us think about it again, which is what is ioctl? Like, why do we have it?
It's a way to communicate with modules.
Yeah, but I can read and write to my kernel module. It is special, but why? Why do we need it? Or why do we want it?
It's a lot easier than doing like read and writing from this thing.
Yeah,
It provides like a shared interface, like an API for doing it.
yeah, exactly. And so basically ioctl allows us to manage our device in a way. So rather than like just reading to the device and going, here's a sequence of commands that I'm going to vomit at you, and then like this device module or this kernel module is now responsible for like parsing every bit of data that you send to this device, and then like trying to like do some massive like you guys took CSE466, right? The compilers class. Remember like how parsing works? Like, do we want to go through that nightmare, or do we just want to have a switch statement that says, hey, if my ioctl number is this, it means that we're doing that. So it's just a very simple way of opening up a complex interface. So like you can think of like, for example, like I have a webcam here. Like if I read from the device, I'm going to get the raw RGB like the raw pixel data from this camera. But if I want to like change its resolution or change its shutter speed or like ISO, like brightness, whatever, then I would want to interact with it in a way that's more intelligent rather than just kind of hoping that it has a parser built into it. Also, this means that if I have 2 different cameras that are slightly different, they might have 2 completely different ways of parsing like this language, as opposed to like a standard interface where I just have to know what all the ioctl numbers are. Okay. So then privilege escalation. So main obvious goal of kernel pwning is to escalate privilege, or at least one of them. And so what I want to ask is like, how does our basic kind of like classic like CRED structure permission escalation attack work? Like, what's the attack vector that we're looking at? Why does it work?
Because the cred structure is stored in the kernel.
Yeah,
So you can,
but what does the CRED structure do?
oh, like ensures like something like seccomp or
So it's basically like this CRED structure, like this task structure for each process that we're dealing with, is essentially controlling what credentials it has in the kernel. Like, what is its access level? What's its permission level? Like, if we're seccomp, it's going to be stored there. Also later, when we talk about how physical memory is mapped to virtual memory, like the task struct is also going to be storing things like the root of like the physical or the virtual base the address of the page tables, for example. Like basically all that process specific information that we want to be able to access quickly. And so when we do this, there's a very simple way to escalate privilege, which is just, hey, I want to make my new task struct base equal to the default one, which is why we do that classic like prepare creds, commit creds with just a 0 there. Like by passing in null, we generate a new cred structure, which by default is just a, hey, full access root privilege, which is kind of funny if you think about it, and we just commit it, right? And so instantly this overwrites our task struct and then says, hey, your process is now root and has all the permissions that you want. Boom, done. And so the question then would be, okay, well, I want to call commit creds. I want to call like prepare and commit creds, right? Like, how do I find the address of these functions? Assuming KASLR is disabled. proc.kl.sims. Something you should be very familiar with at this point is the proc.kl.sims file. Okay. So we just said KASLR. Who knows what the heck KASLR is?
The ASLR for kernel.
Exactly, literally, just kernel ASLR. So now the question is why and how is this different from user space ASLR? Because the differences here are actually very important.
The kernel only exists one time, so it's only going to be randomized once.
That is very true. The kernel exists once, and when the kernel stops existing, our computer shuts down. So, therefore, when we're attacking the kernel, we can use as many processes as we want to try and leak things out of the kernel, because once we have that leak, it's not going to change until we reboot the kernel, or essentially reboot our computer. And so this makes pwning interesting from the fact that, like, hey, I can have one attack that's doing this one thing, and then I can have this completely separate process that's doing another thing. So you could think of like having one process that's maybe like, I don't know, doing some like insane like 0-day to leak something out of the kernel, and then you have another process that's doing some more traditional kernel exploitation, which you can leverage like once you have all these symbols, right? And there's one other thing about kernel ASLR that I think is really important to remember, which is that there's no sections in the kernel. Like the kernel is loaded once and it's all contiguous. So when the base address gets randomized, we're back in the same position where it's like, remember back like in the good old days when we're ropping, right? And so when we leak one address in libc, we know where everything in libc is. Similarly to the kernel, when we leak one address in the kernel, we know where everything in the kernel is because it's all relative to just one base address. And so knowing those differences is important, and it makes your life a lot easier when you're exploiting, when you don't have to like constantly rethink about, oh, the memory address has changed. Like my process crashed. Like it's not that bad. Any questions about KASLR? Cool. Okay. Next, process memory. So this is one where like you're not going to be asked to like dredge out the nitty-gritty specifics of the entire process on the final, but you should have rough ideas of how these processes work. So, for example, like how are virtual addresses mapped to physical addresses? Like what's the mechanism that does this?
FISMAP?
FISMAP. Well, that's one of them, but that's the FISMAP is basically the physical memory or the mapping of all of the physical memory in the kernel, right?
So like the HUD, PGD, P4D. But what?
Page tables.
Yeah, the page tables.
Yeah. So we use page tables to basically map virtual memory to physical memory. And so this process, like this looks like basically grabbing things like that CR3 register, grabbing basically that first address from the task struct of the first page table, and basically performing that walk, right? Where you basically use the different components of your memory address to walk through those page tables and get to that final physical location. If you aren't familiar with that process, I would highly recommend going and looking at the lecture that we have on that, and then pretty much just having a rough understanding of how that process works. You're not going to be asked to do like a page walk from scratch, for example, but you should know what a page table is and how it's used. So similarly, when we use virtual memory and physical memory, it's very possible that we can have 15 virtual pages that all map to the same physical page, right? Why? And this gets at my second question, which is what is copy on write? Like why can we do this?
They could all be just reading from that page, so there's no need to copy it. Recently done.
Exactly. So like, for example, let's say that I have like a read-only configuration file and then I map it into memory and I have 5 processes that all use the same configuration file. Like they don't need to each maintain their own separate copy of the same read-only data. So we can basically our CPU, or sorry, not CPU, but basically our kernel can make the assumption that, hey, only actually make a new physical page of memory for this data once it's modified in any way. So that's what copy on write does. And so this means that like, if I have 5 instances, like 5 virtual memory pages all pointing to the same physical page, and then one of them makes a modification, then that's going to cause a new physical page to be copied over. And so now you have 2 instances. It's just they're both different now. And then so finally, FISMAP. So remember that in the kernel, like the kernel wants fast access to physical memory. And it doesn't want to bother going through translation processes every single time in order to translate virtual to physical memory addresses and then like deal with like all the song and dance. And so instead, we just map all of physical memory into the kernel, which is fun, right? And so who can tell me like why this is useful as an attacker? Like what are the implications of just having all of physical memory accessible from the kernel?
We just need to know one address and we know like everything else.
Well, so that's one thing, is that like it's a contiguous region. So once we know like once we know where the phys map is located, we can easily get to other places. But once we can get to other places, what are the implications? Like, what can we do?
We can scan it for sensitive information.
Yeah, so we can scan through memory for sensitive information. But because we're in the kernel, what else can we do? Like, what's stopping us from just messing with things in the phys map? It turns out there's not a lot. In fact, it's pretty much just like your own free will. And so by modifying the phys map, like we can go in and literally change the memory of other processes. Like, y'all are gamers, right? Like, surely, like we have experimented with the concept of using one process to modify the memory of another process. For example, like cheat engine or something like that, or injecting a DLL into a process. Like, so when you're in the kernel, like you have this phys map region, which is all of your physical memory, and you could just go in and arbitrarily modify things. Like, so you can cheat in video games, or you can, like, as we said, like read like crypto keys, or even corrupt them if we wanted to. Like, just lots of fun things. And so next, kernel shellcoding. So this is pretty simple, but basically there is a difference when you are shellcoding and targeting the kernel versus when you are shellcoding and targeting a process in user space. What do those differences look like? Anyone? Like, what can we not do in the kernel?
Syscall.
Yeah, there's one.
So you have to do like move rex, call rex.
Yeah. So rather than like using our system call numbers in the kernel, like instead we have to go and physically find all the addresses of these places that we want to be, and then indirectly call them around. And so we're a little bit more software developy, I guess, for lack of a better term. What else do we need to do when we shellcode in the kernel?
Not have your code blow up.
Yeah, not have your code blow up. That's a very, very good thing. So, but what does this imply that you need to do at the end?
Exit return.
Yeah, so we need to be able to return from our shellcode. It's in the kernel. Because if we just start executing shellcode in the kernel and we treat it like we've been treating user space code, which is just, hey, it opens, reads, writes the flag, and then it can crash. I don't care because it's on my screen. When you do this in the kernel, your kernel panics and then you have a problem. And so you need to be able to return cleanly from the shellcode that you're writing in the kernel. So those are just like the main two differences. Really quite simple, honestly. I think that's the last thing. So like these are all of the like rough concepts that are going to be covered from Greenbelt on the final. Like obviously not every single thing here is going to be on the final. Obviously, like I did not just give you every single answer on the final as well. So, but that's roughly what you can expect. And so the last thing I want to do is just kind of give like a quick little microarch demo. So one question that I got more than once was, how do you pick a timing threshold for like microarch? And we're going to run through this demo a little bit just because we're running out of time. But let's see. So I guess there's two things I actually wanted to demo. The first off is that when you are doing these attacks, you generally want to try to be on the same CPU core as your victim process. Meaning, so like if you have an attacker and a victim process, like you're trying to perform a speculative execution attack, you want them to be on the same CPU core. And this is important because if you just willy-nilly just decide like, hey, I'm not going to worry about this, it'll just sort itself out on the back end, right? No. Because what ends up happening is anytime your process goes through a context switch, it's like the CPU needs to start executing someone else's microarch code that's like slamming the CPU, then you can potentially get moved to a different core. And Robert put a sweet little bit of demo code in the Discord about this that I just wanted to like quickly highlight. If this window would, there we go. So very, very simple code, just schedule get CPU, like here's what CPU we're running on. And we're going to do this in a loop, and we're going to sleep 1 second, which that sleep is going to trigger a context switch, essentially, because we're saying, hey, park this process in place for 1 second, don't touch it. And so when we run this, which I've already built it. Oh, no, it's in the wrong directory. When we run this, we can see that as my process sleeps, it's going to be jumping around cores, or at least sometimes. The point is that you can't guarantee this from like not happening. I swear this was different every time. Yeah, there we go. Okay. That's normally about what it looks like. Especially on like a more busy system, like where you're straining all of your cores, like it's going to jump around even more often. And so the way we dodge this is by using this fancy code that I prepped ahead of time, which is basically pinning the CPU by setting the CPU affinity for this specific process. And so pretty much it's just this little helper function here. Yeah, essentially, like pretty much you define a CPU set, you say, hey, I want this to go on this specific CPU, and then we use the scheduler to set the affinity of it. And so in this case, I can just type pin CPU 0, and this is going to park this process directly on CPU 0. And so if I take this same loop, put it right here, we are going to see after I build this that we are, oh, that's the wrong one. I need to build template. Got it. Okay. So then let me make sure to run the right file too. So now, no matter how much we context switch this process, we've told the CPU, hey, this goes on CPU 0, no matter what. So now it's not going to like just willy-nilly move it around to wherever it wants to go. Like it's going to be on CPU 0. That being said, like you don't have to use CPU 0. Like we can come in here and pick like whatever core we want. So I believe like this is a 40-core machine. So I have to rebuild. So it should go all the way up to 39. So yeah. And so just play around with that. Like obviously if you all pick CPU 0, you're all going to pin the same CPU and then it's going to be harder. But yes,
What happens if you went outside of the 40 CPUs that exist?
it's just not going to work. So
Will it just die?
I'm actually not sure. I've never tried it in practice. I believe it just will park it on whatever it can try. I don't know. I believe it's just random.
Huh.
But yeah. Okay. So let's see. I am going to speedrun some code. Okay. So what I wanted to do was basically talk about how to pick a timing window for when we're doing a speculative execution attack. So like when we're looking at like that flush and reloading technique, like what is the threshold that I know, like, hey, like this is the cache row that hit versus this is the cache row that missed, because we're timing them, right? And we're timing them based on CPU cycles. And so we know that when we miss the cache, it's going to have to go out to our main memory and fetch that information. And so it should, in theory, take longer. And so I personally think this is really cool to visualize. And so we're going to hack together a very fast demo. And so basically what I prepped ahead of time is a script that goes through and it's going to graph data. How the graphing works doesn't matter. And so instead, we're going to write some code. So basically, I've loaded up Baby Spectre 4 just because it's a good demo program for this one. And essentially, we are going to use this to basically force a cache hit to constantly happen. And then we're going to then flush the cache every single time and then measure. So we're going to measure a whole bunch of hits, and then we're going to measure a whole bunch of misses, and then essentially just see what happens. And so first thing we're going to do is let's make just a buffer of data. So 32, sure. Do. And then we're going to go ahead and put this value. All right, I think I need to set it to something. Let's set it to something just in case. And then that should be fine. A. Oh, you can. All right. So then we need to get this value into the cache. So we're just gonna make a really long loop. I less than 5,000, I plus plus. And then we are just simply going to access this repeatedly by just throwing it in the code. Boom. Accessing. This counts. Basically, we're just going to cast to a void and then dump it into the ether. And so by doing this 5,000 times, we've hopefully populated this value in our CPU cache. And so now that it's in the cache, let's go ahead and measure how long it takes to do this. And so we're going to need another loop. And let's say that we measure this 10,000 times. All right. And so we're going to, oh, that's not how I code. So we're once again going to take the same access. And then we need to measure timing. So now timing in access is always fun. And so I always like to kind of spin it off as its own function, just because we're going to have to use it again. And so has anyone actually written a successful timing function? Oh, what can't fix it? There we go. So hopefully some of you guys have gone through and like solved some of these baby specter challenges already. Like, how do we time a memory access properly? Like, what are the functions that we're using?
CC and then alpha.
So we have our fencing functions like mfence and lfence, and then we have basically our timing function, which is rdtsc. And so let's say, I think this is like a uint64t that returns. Let's say time it. And then let's say we want to access memory. So we'll give ourselves that char pointer. That's not how we define function. Neither is that. Okay. And so what do our mfence and lfences do? Anyone?
I believe the L fence guarantees that all loads on that memory address before the L fence will happen, like, will not be speculated on. So like anything after that L fence, sorry, it would be before the L fence, any load on it will be guaranteed to happen before your load.
Yes. So basically we're saying, hey, when we put this L fence down, the loads before this have to finish. Like everything's got to be clean. Like we're basically prepping a clean slate so that we make sure that nothing's happening in progress. It's not trying to like transiently speculate this on ahead of time, which could in theory mess up our timings. So basically I'm going to throw down an mfence. Mfence basically says, hey, ensure all previous memory loads are done. Lfence, once again, just making sure that that's done. And basically we're serializing execution, like as you said. And so from here, we want to measure our timings. And so I'm going to define some variables up at the top. So you can add a start time, we need an end time. And then, as you said, we're going to use that rdtsc function to time. So I think it's 2 underscores. Or no, I think it's rdtsc, right? Yeah. Because it's like read ts something. Anyway, so there's our start time. Now we need to make sure that all of our memory fences, all our loads are done again. So I'm going to do another fence. And then here we actually perform our access. So in this case, I want to basically just grab our address. So we're going to dereference that. So we're going to grab the basically the value that that's pointing to. I need to define this and say char temp. There we go. And then we're just going to touch it. And the reason we're touching it, by the way, is to prevent the load from being basically like compiler optimized out. Because if we just load something, we don't do something with it, the compiler is going to go, why are you doing that? And it's going to think it knows better than you. So you have to be careful. And so finally, we mfence again, because we want to make sure that this load finishes before we actually pull our end time.
And then
Oh, thank you. So rather than measuring the start time, we're going to measure the end time. And then big end, where did that come from? There we go. And then one more memory fence just for good measure. And then finally, we can just return the differences between those end minus start. So once again, to summarize basically what's going on here, making sure that all memory accesses are done. And then we are going to lfence, which basically make sure that things happen in order. We start timing, make sure that finishes. Then we perform our access, make sure that access actually finishes. And then we take our end time. And this is basically the way that we can ensure that we're timing just that very specific action. And then finally, we just take the difference between the two to figure out how many CPU cycles that process took. And so now down here, when we're actually measuring again, so here we have primed the cache with a value, and then we are going to measure what those cache hits look like. And so we can say, let's see, I think it was like uint64t. And then we'll say, I guess, elapsed is going to be equal to time it. And then we are giving buff as the pointer. And note that I'm giving buff. So then this access is going to be that index 0 that we have been priming. And then finally, we're just going to print this out. So I'll say like print, I'll say this was a miss. And then let's see, %u for an unsigned value, and then elapsed. And so we could test this now, but we're going to blaze ahead and just hope it works. And then we're going to take the similar loop, right? Now, how do we evict something from the cache? Like what's the function that we use to flush?
CL flush.
So we are going to call it one underscore CL flush. And then we are just going to simply provide that void pointer of buff. And then we no longer are accessing it because we don't want it to be in the cache. And then we are going to make sure that that finishes with an endfence. And this time, oh, I guess this first one would be a cache hit, not a miss. All right. And so in theory, now we should have this long list of hits that comes out and this long list of misses that comes out. And then we'll exit out. And basically I have this Python file that's going to graph all this, and it's expecting a CSV file. And so we're going to put a CSV header at the very top. So we are just going to say, let's call it label and then cycles. I need to put an app after this. All right, that's just plumbing. Don't worry about that. So I'm going to build this template.co template. Oops. Oh, I put double underscores in front of a lot of those. Hold on. We can fix that. 1, 2, 3, 4, 5. I think that one's right. Why they have different amount of underscores in front of them is something I don't know, but it's something I kind of want to find out now. And so then we should have this, but obviously we need to actually give this to our challenge. So template, and then this is going to output all that data. And so I want to send this to a file. So we're going to say timing, or wait, I named it something. I hard coded the name in this, cache timings.csv. And then we give that some time. Then, ooh, it might not actually exit properly when I do it like that. Let's do, let's say, is it there? Oh, okay, I guess it's there. VS Code is not updating. Oh no. All right, there we go. Manual surgery to get rid of the yawn garbage. But as you can see, like our hit values are pretty low. And if we scroll all the way down to where our misses are, you can see the value drastically jumps. And I personally think it's very cool to visualize this. And so if I run my Python function to visualize this, it's going to generate a graph over here. And basically, we can generate a histogram of what basically these look like. So we can look at the probability distribution of what these timings look like. And so when you measure all of these, like our hits are in blue, misses are in orange, like there's a very clear separation between these. And so as long as your timing threshold is able to differentiate from basically these two blobs of data, then you're good. And so that's kind of how you can like experimentally figure out like what that timing threshold should be. So like based on this graph, I would probably pick something that's maybe right around that like 210, 220 mark, because you generally want to put it closer to this orange bunch than the blue bunch, just because you're looking for things less than that. So you want to give yourself a little bit of a bigger window. Because if we zoom in a little bit, it's hard to see because I sampled like so many times, like 10,000 each. But there are some little blue specks kind of out here to the right. Like it's not always guaranteed to take right in this like what looks to be like the 60, 70, 80 millisecond mark. Like we can't have some go longer. Similarly, we can't have some cache misses that seem to take a little bit less time than the rest of them. And also you will have outliers. Like we have things that are all the way over here. But they're all misses. And so this is just something that I think is a little bit cool to visualize and just kind of dig into. Yeah, it is like Portal.
The video game.
All right. So anything else before we round out? Any questions about this?
Can you zoom in on the things past 800?
Yes. We could also look at the raw data if you wanted to find out if there was one. But there, for example, is two little tiny orange bars all the way over here. So those were some very egregious cache misses. As for why it happens, like CPU stress, like lots of different things. Generally, like when you're trying to do these like microarchitecture attacks, it's just trying to build up your like, I guess like resiliency almost, where you want your threshold essentially to be able to differentiate between these two groups. And if you run this and it turns out, hey, both of these like if I ran this and both of these were completely overlapping with each other, that's telling me that something's wrong. And so you should be able to differentiate between these two. Okay, cool. That's class.